which means that you don't have to worry installing all the tooling like the Haskell compiler and so on yourself. You can just, with the Open Visual Studio, it asks you whether you want to open the project in the dev container, and then if you say yes, then you have an environment. Everybody has the same environment with all the tooling you need. Unfortunately, I realized that too late. So, and the first time you do it, it takes a while. But I'm already in the last step, so hopefully should be finished soon.
Lars, while we wait, Segun David has a question.
Okay, yes, please go ahead.
Segun? Not sure if you know Segun, but you're muted, or maybe you can type the question in the chat. Yes, he's trying to ask the question. Let's give him 1 minute.
Of course, it's still installing stylish skill anyway. So last time on Monday, I was using my local setup, which also works, but probably it's better to use the one that everybody else will also have. Then there won't be any discrepancies between what you see me doing or what will happen when you do it yourself.
Yeah.
And as I said, the first time it takes a couple of minutes, but then as long as we don't change the dev container configuration, it should be almost instantaneous the next time because it's cached. And I think that's also exactly the same environment if you do it on GitHub. Sorry, go ahead.
It's just a query in regards to a GitHub issue where some learners were not able to access the assignment.
Oh, okay.
Can you Lars open the repo to show them like when like they have to go to the did you find, Segun David, did you find the link? Because we have right now 13 students that already started the assignment, and a couple of them already sent the responses. The second part of last lesson is not clear, and I could.
We are talking about
the main repo. Cardano, yes, this one.
Yeah, I mean, yeah. Hello, Lars.
Hello.
Yeah, fine. Good day to you. So,
thank you. To you.
Yeah, almost a layman when it has to do with these coding of a thing. But just that, in my undergraduate days, I think I have some preliminary experience, and I've been a passionate crypto enthusiast since I think 2016 or thereabouts, because I could remember days of BNB when it was still sold for 0.1 pounds, $0.1 rather, beneficiary, and ever since then I've been on track. So getting to know about blockchain, Cardano blockchain development project, I think I'm not new to hearing Cardano, but I've been so curious at knowing these these blockchain development aspects of it. So that is one of the major reasons why I wanted to give it all in for this program.
Okay.
But I discovered that when you started the teaching yesterday, I think there are some background that I expected to see in the course of the teaching, which I couldn't. And in addition, these are the assignment that you gave to us. Initially on my GitHub account, I saw it. Later, I couldn't find it anymore. So, but I tried going through the video, through the slide over and over again. I couldn't really pick what is going on in the class, which I would like to be, as in to know more I would like if there are some literature or some. I initially know that at least using my chat GPT to be able to learn some one or two things via the platform. But in class, then if there is any additional literature document that you can share with me or people like me in this class, it will go a long way helping us to become a better student taking this course.
Right. I mean, first of all, I don't think that there are any requirements. So you're not expected to know anything about blockchain or programming. I mean, sometimes it can even be a hindrance if you are very experienced in a more traditional programming language like TypeScript. It can actually be an obstacle to learning Haskell because the mindset in Haskell programming is completely different to the mindset in most programming languages. So you don't have to worry that we expect stuff. As for literature, I mean, we don't expect anything. I always personally, I like this Learn Your Haskell for Great Good. I can open that. If you just Google Learn Your Haskell for Great Good, it's available as a book, but it's also available online for free. And this doesn't go very deep, so we will probably cover all of this in the first 2-3 weeks of the class. But nevertheless, I think it's a very gentle and entertaining introduction into Haskell. So if you want something beside the course. But apart from that, we don't expect any prior knowledge, really. And so what was the problem with people not getting access?
I wanted to show that how you can do it so they can see. But
Right.
if you scroll to the outline, you will see the A1 link.
Yes.
Yes, there. And
So if I just click on it,
yeah,
then
Yeah.
I have to authorize, and then I can accept the assignment.
and now you have to
And-
wait. Now the repository is getting set up, but because it's super like lightweight, likely if you refresh now, you will have the repository ready.
Let's try that.
There you go.
Yeah.
You can clone
And
it
now
or open.
So I could either clone it or I could just online.
Yeah.
But that's probably my setup.
Yes.
Some weird. The same reason I couldn't talk in Zoom last time, probably.
Right.
But even if that happens to you, I could just clone this repo, right? And then.
Yeah.
And it's tailor-made for me, so it has my name. So
Exactly.
everybody gets his own repo.
And whenever you push a change, we'll get the update.
Right.
And that's it.
Okay.
If you open that repository in VS Code with the development environment extension, you will get the prompt that Lars got that now is getting install everything.
Let me just, so if I copy that and go to my, open a terminal window and just, okay, if I clone it, okay. Okay, and now I'm inside that folder that I just cloned. If I just start Visual Studio Code, yeah, I trust myself, and now I can do this reopen in container, and that's what I just said. What also happened to me that now the environment will be built, but this time it was very fast. So maybe not. Shouldn't it be used? It's probably the same one.
Yep.
So that should be fast.
Oh,
okay.
No.
It's the same that's still going on my other side. But it doesn't do, I mean, you don't have to wait long for every single assignment because it obviously realizes it's the same container, so it only builds it once.
Yeah, actually, installing stylish Haskell is the thing that takes the most time. So maybe we could add the binary directly. That's it.
Yes, maybe, probably should.
You may want to
Yeah.
close one of
But now
the
it's,
repos.
yeah, but now it's building actually stylish Haskell, so now it should hopefully be done immediately. Installing now the executable for it. Should only be a matter of very few seconds now. Yeah. So now it's installing it and okay. And now it's just cleaning up the Docker stuff. Whatever that means. Okay. Now and there we are. Okay, so now the environment is ready. But if I now close this here and open it again, and again say reopening container, then it's almost instantaneously. And now I could start working. So in this case, so this would now be the assignments. I'm not sure, do we have to download stack?
No, no needed. Should be able to build right off the bat.
Okay. Okay, so yeah, that's should be relatively easy. Okay, so let me close this now and switch back to my other. This is now also done. We just go into the right folder. Okay, so this is where we, okay, let's not. Right, so it always takes a while until these extensions install. So right now, when I hover here over something, I don't get any IntelliSense, but that should hopefully come at some point.
Yeah, below says processing 1 of 2.
Yeah.
Yeah.
Right. Yes. I don't know whether one should. Isn't it necessary for this language support and server support?
No, it's not necessary. But I mean, if it keeps prompting, you can install it. It shouldn't make a difference.
Right. Okay. Anyway, so so this is what we had last time. So we defined this data type as a first example of how to define the data type in Haskell. This chain data type, two constructors, Genesis block and block, which takes Genesis block takes no arguments, block takes 2. You also saw how you can give new names to existing types. Oh, now this thing is working. So now I get, I mean, this is actually luxury. You are very lucky because until a few years ago, none of that existed. So there was no like nice editor support where you just hover over something and you see information. So you had to do everything in the REPL actually. So nowadays, this, I mean, when I do now this :I chain, for example, for information, sorry. Sorry, I'm not in the folder. I must be in the folder for this to work. So if I do this :I chain, I mean, this is now basically the same information that you see when I just hover over this, more or less similar. And so this is relatively new. I mean, one of the big complaints about Haskell in the older days was that the tooling was so bad. So it was, I mean, you didn't have graphical development environments like. But nowadays, this integration with Visual Studio is really nice, and you can do lots of things that were quite painful in the past. So in the past, basically, you had to make do with what the REPL could give you. Okay, we defined some example chains, and our very first function, chain length, to compute the length of a chain, and then another function that checks whether a given block, which is just a synonym for integer, is in the chain. I talked briefly about operators, so we can make stuff look nicer by using this this operator instead of the block constructor. And we generalized this hasBlock a bit to hasBlock prop with this function that takes a predicate. That was an example for higher order function. I think last time I didn't say what actually means higher order function. So by definition, function is higher order if either one of the argument types or the return type is again the function. So in this case, and strictly speaking, because we said we talked about currying, so we said that this type is actually the same as that because the function arrow associates to the right. So by the definition for higher order function I just gave you, this also would be a higher order function because it has a function result type. So strictly speaking, every Haskell function with more than one argument is a higher order function. But normally, I mean, this is not very clearly defined, but normally when people talk about higher order function, they are not talking about just functions with more than one argument, but more about something like this, which takes a function as an input. Right. And I just want to stress again that, so, I mean, I decided to not rush through the lecture, even though it's just an introductory lecture. I mean, I think it's important that rather we spend some more time in the beginning and then become faster later, because the foundations are, of course, important. Nevertheless, it's just an introduction that should give you some idea or flair of how Haskell is different to other languages. So all the things we touch in this lecture will be repeated in much more detail in following lectures. So you don't have to worry if you don't understand everything yet. It's just meant to give you like an overview of some of the interesting features of Haskell. So one thing we want to do next now is talk about parameterized types. So if I go to the slides, let me just, that's I think I believe where we stopped. So parametric polymorphism. That is something you probably also know from, I mean, if you know TypeScript or Java or C# or even C++. I mean, in the old days when I started professional programming C#, it just started that, I mean, there were basically a list was just a list of objects. And if you wanted, there was nothing for like list of ints or list of floats or list of whatever. So you had to use a list of objects and then always cast the elements to the type you knew was in there, like int. But then very soon, like, I don't know, 15 years ago, so in most mainstream languages, they started with generics, it was called in C#, where you can have list of integer or list of character or list of Boolean. So you define the list type once, and then there's a parameter for the type of elements. So that's actually quite a common concept in other mainstream languages as well these days. And Haskell has always had that. And so one example is now we generalize this payload. So here we always had this payload that we call TXS, which was just another name for int. Let's say we want to consider chains that have other types of payloads, not just int. So the way you can do that in Haskell is like this. So before we just had this chain type, it was just this word chain. We defined the chain data type. Now this becomes gets an argument, which we here call TXS with a small lowercase t. And so the idea is now this is a chain with payload of this type, where this can be an arbitrary type. And again, two constructors, Genesis block, no arguments, and block with the beginning of the chain and the payload. And the beginning of the chain now is also has the same parameter. I think I also didn't mention that last time. Lowercase and uppercase is important in Haskell. So we see that the type here, chain, is in uppercase, and the constructor names have uppercase. If we go back to the code, we see that expressions, values, like my favorite int, but also functions start with a lowercase. So it's always like that in Haskell. Values, functions start with a lowercase, and types and constructors start with an uppercase. And variables start with a lowercase. So this here, this lowercase TXS, because it's a lowercase, you already know it's a variable. So it's a so-called type variable. So what we can do is we can just change this here, or I could, maybe it's better to copy it and not mess with the existing code. So let me just change this and call it polymorphism. And we don't have to worry about Cabal files yet. But in order for this to work, I have to mention this here. And I also have to reload my REPL. I will get an error because I forgot to change the module name. I mean, we'll talk about the layout of a Haskell project later, but in Haskell, there's a one-to-one correspondence between source files and modules. So each source file corresponds to exactly one module, and the name of the module must be the same as the file name. So the module is called polymorphism. The file name is called polymorphism.hs. Okay, so now this should, if I reload now, I shouldn't get an error anymore. Let me load this. I can load a specific module with :L for load. Okay. So let's change this type polymorphic. So we give it a type parameter and say, so now we don't just look at integer payloads, but at arbitrary payloads of type TXS. So I can remove this definition. Now, if I, for some reason, it hasn't caught, yeah, I must save, but it hasn't. Do we know why it starts to fail?
I'm not sure, but I will look at it. I will take a look at it after the list.
I mean, I have a local setup that works. Let me just reload this outside. I mean, just with my local setup. So this time, yes, I still trust the authors. But this time I just say no when I'm asked whether I want to reopen it in the container. Oh, no, sorry. Sorry. I'm one level too high. What was it? Haskell put this 24. Several levels too high in my folder. Sorry about that. So
Just
this time,
just as a comment for the students, you can still use the containers. Stylish Haskell is just like a formatter that makes it look nice, but it doesn't change the meaning of the code.
Right. So it's not, But let me just now not open it in the container. So now I'm like in my local setup. Should look, it should look exactly the same, but the stylish Haskell stuff, for example, should work. What was it? Polymorphism. Why? Sorry. Something wrong. Just a second.
Permission denied.
That's this.
Yes, the inside is root.
Oh yeah. Okay. Let me just. Why not? Why can't I? It's one level higher. Sorry. Okay. Now it works again. So it's sometimes a bit weird because these containers, I mean, you are a root user in the container, and so sometimes there can be like these permission problems if you switch between local development, container development. So normally you shouldn't do what I just did and switch between those. You should like decide on one and then stick with it. Anyway, so let's see. And sometimes it helps reloading. No, I don't want. Because I mean, right now I don't get this port, but I should at some point. Now it's processing, whatever. Now I have it. Okay, so now I got some errors. So let's see. Line 25. I mean, now I have to, actually I should get errors for this as well, but let's just fix one after the other. So, I mean, I know that you get an error, but I mean, let's pretend I'm you. So I reload. And this is a bit bigger. So I get a bunch of errors now, which is to be expected because I made a significant change. I mean, I changed this chain type. Oh, no, sorry. I'm in the wrong file. Right. I changed this chain type to now take the type parameter here. So it's not surprising that I get errors. So let's see. The first one is in line 25, and it says not in scope, type constructor, or class TXS, which is not surprising because I removed this definition of TXS because now I want to be able to treat all sorts of payloads, not just this capital TXS type. So obviously it can't know what that is now. So let me just change it to a lowercase. So this seems now to have worked. So that means this, or at least it looks like that. Actually, okay, let's just do the obvious ones, change all the uppercase. Okay, so now I get more errors because chain doesn't make sense now anymore. Now I always have I need this argument, the type of payloads. So let me just write a TXS here and the TXS there and the TXS here and the TXS here. I mean, this is something like, like in C#, so it would be list. I'm not sure what the syntax was, something like T or list int or in other languages. I mean, often it's written with these Angular brackets, so maybe you know that from other languages. Right, so let's first do this. That's the obvious thing. Sorry. Editor problems sometimes. Okay, so now I fixed those things. Right, now it's complaining. For example, I could go by editor and do the squiggles, or I can go by what the REPL tells me. Oh yeah, and they tell me different things because I forgot to save. So let's save and reload. For some reason, I can't type today. It's okay. This is again this. It's a permission problem. Just a second. Sorry about that. So it belongs to me, but I think it must belong. Oh, that's a bit. Oh yeah, no. Source. Right. So I am Broniela, but this thing now belongs to the root user. So that comes from the container. So I must sorry, I mean, you would never have problems like that. That has nothing to do with Haskell. That's just this container stuff. So now it worked. So now I can save. Sorry. So I just changed the ownership of this file to my non-privileged user. Okay, so let's try this again. Capal REPL. Load the polymorphism module, and let's see. So we get a bunch of other errors now. Right, so let's start at the top 10. So this is now, I try to generalize this now to our new type of chains that can have arbitrary payload. So basically what this line signature is saying is chain 2 is a chain for an arbitrary type of payload. But then when I define it, I have this 4 here, and the 4 is clearly a number and not some arbitrary type. So that, I mean, that wouldn't make sense to say this is a chain of arbitrary payload because it's for a specific one. The 4 makes sense. So for example, I can change this to the specific type int. So I can say this is a chain int. I can do the same here, here, and here in our concrete chains. So they also see how that's done. I mean, this is like a schema for types. So you have a chain int, you have a chain character, you have a chain bool, you have a chain whatever. And if I want to define a specific chain with a specific payload type, the notation is like this. So it's chain int means it's now a chain where this lowercase txs is int. So in the block constructor, in particular, the second argument is an int. If I write chain character or a chain bool, for example, then in the block constructor, this txs would be bool, so it would need to be true or false. Anyway, so this is now fixed, those errors. Now we're almost done, but not completely. There's one error remaining in 27, and it's complaining about the equal sign. And what's the problem here? I mean, earlier that compiled without problem when we were specializing to integer payloads. But now this we get an error here, and the reason is that in Haskell, not every the element arbitrary types are not comparable with each other. I mean, you can compare two integers. So if I have 3 of type integer, I can check whether it equals 4, which is false, but it does equal 3. It's fine. Same for Boolean. I can ask whether false equals true, which is false, or whether false equals false, which is true. But equality is not defined for all types. In particular, it's not defined for function types. So there's no way to check whether two given functions are equal. So Haskell refuses to compile this because I don't know how to compare an arbitrary element, two arbitrary elements, one called n, one called x, of type txs for equality if I don't know anything about this txs type. So now similar to what in some languages is called interfaces, like in .NET and C#, it's called an interface. Something like that exists in Haskell as well. It's called type classes in Haskell. And that means you can say that, for example, for specific types, equality is defined. So the notation for that in this case is this. So we will have a whole lecture on type classes. So I don't want to go into detail now. But what this addition here means, provided you can compare elements of type txs for equality, then we can define the hasBlock function like this. So this is now, I mean, for example, chain length is defined, sorry about this IntelliSense block. So chain length is defined for chains with arbitrary payload type. The chain length function doesn't care what txs is. So I can generally define that. It's a completely polymorphic definition for chains of any payload type txs. hasBlock is different. It's not defined for arbitrary chains, but only for chains where the payload type can be compared for equality. And I think that was the last error in this. So yeah, now it compiles. So for example, if I have, I mean, I can have hasBlock, I mean, as before, then let's say 3 integer. What was that? What was the notation? I'm just trying to think left. So Genesis block 1, 4, 3, for example. It's true, but 7 is not. But now it also works for other types, not just int, that have comparison for equality. And we just saw here that Boolean is such a type. So for example, I can now say something like hasBlock true, and this is block Sorry. True. And then this block. False. False. True. This is true because it does have a payload true here. But if I, for example, change this to a false as well, then it becomes false. So now it works for arbitrary things. But if I take a type that doesn't have equality comparison, for example, if I use a function, let's say plus int, then it complains that the type of functions from int to int doesn't have is not an instance of the equality type, which means you can't compare things like this for equality, and therefore, but I'm only allowed to use types that have equality if I want to use the hasBlock function. So there's that. Let me see the slides. So we talked about this, that some functions now they just work for every choice PXS. Others do not, and we need this so-called class constraint, equality class constraint. And I showed you that and demonstrated that. Okay, so that's that. That was a short teaser on polymorphism. Now another thing that's it's more or less historic in functional languages. It's not just Haskell. I mean, Haskell has a proud ancestry going back to the very first high-level languages. Lisp. I think Lisp was one of the Fortran and Lisp were like the oldest higher programming languages, and Lisp is called Lisp because it's list processing. So lists have always been very important for functional programming. And the same is true in Haskell. So in Haskell, lists are also very important. And sorry, I know why I wanted to. So if we look at this, for example, I mean, we see this is, I mean, somehow what we call a chain, what we defined here as our toy type to play with, this chain type. It looks, I mean, this thing looks very much like a list of 3 ints, 3, 4, 1. I mean, it's the other way around, and it's somehow, I mean, has these funny symbols and the Genesis block stuff, but more or less it's basically a list. I mean, what we defined here, this chain, it's more or less just a list of payloads. And lists, as I said, are especially historically very important in Haskell, and they are like the workhorse of Haskell. So basically, you work with lists all the time to do stuff in Haskell. And let me go back to the slides. So because they are so important in Haskell, there is syntactic sugar for lists. So normally we just learned that types always start with this capital letter. And if a type has arguments, it's the name of the type, like chain, and then the name of the argument. For list, there is a special notation in Haskell. And the special notation is square brackets around the element type. So this type in Haskell is the type of lists where the elements, the lists have type A. So in particular, Haskell only has, or at least like built in, these lists are so-called homogeneous lists where all the elements have the same type. I mean, in JavaScript also, if you have a JavaScript array, you can put a Boolean in and then int and then whatever, a string. In Haskell, all the list elements have the same type. So the notation is this. And here you see basically the parallels. So for our chain type, we had 2 constructors, one to basically give the empty chain with no payloads, and then the block constructor with given a chain and 1 additional payload constructs a longer chain. I mean, that consists of the whole chain and then this payload tagged on. And similar for lists, so we have this thing, That's the empty list. So the empty square brackets represent the empty list. And we have the colon operator. And if you notice, it's a little bit the other way around. So block constructor, we first had the recursive argument, the chain, and then the payload. And here it's the other way around. This is pronounced cons. So cons, you first have the element, then the list, and then you construct a new list. So this is also called the head of the list, and this is called the tail of the list. So given a head and a tail, you construct a new list. And so if we have a chain int that you find like this, so Genesis block, then the block constructor taking on a payload 1, and again applying block constructor with payload 2, this would basically correspond to a list of type int, 2 cons to 1 cons to this nil or empty list, which is also sometimes called nil. So for historical reasons. So maybe we can do this. A list. What was it? 2 colon 1 colon empty list. I reload. Was it this one? Yes. Okay. So now I can also, as I said before, in the REPL, we can always ask for information. If I ask for information about an operator, I must put it in parentheses. So we see the type here. And in particular, we see it's right associative, which means these parentheses I can leave out, and that won't change the meaning. So I can also write it like this. And there's still a blue squiggle, and the blue squiggle, I mean, the way of my editor telling me that somehow I can write that nicer. And that is because lists in Haskell, I mean, we already saw some syntactic sugar, that the type of list is written with these square brackets around. And this nil is also like syntactic sugar. It's not a normal name for constructor. And there's another piece of syntactic sugar for lists. So equivalently, I can write this as follows, just like, sorry. I can write it like this. So square brackets and then just listing the elements. And actually, when I have it shown to me in the REPL, it is displayed in this way. So if I change that back to what I had before, this, for example, if I reload and ask for a list again, it displays it in exactly the same way. So that's exactly the same. It's really just syntactic sugar. It doesn't change the meaning. It's just, I mean, the compiler or the parser or whoever, it gets translated to compiled to exactly the same code. It's just a more convenient way to write lists. And it also nicely goes with this symbol for the empty list. So it's consistent with that. So there are these two ways to write this. So I can also write it like that. This, by the way, this minus minus is one way to write comments, like line comments in Haskell. That only stretch from you have the symbol to the end of the line. There's also block comments in Haskell there with curly bracket minus, and then closed with with minus closing curly bracket. So this would put this whole block as comment. That's convenient if you want to comment out some code. I mean, it's more convenient than having to put minus minus in front of every line. Just as a side note. Okay, so that's lists. Right, and I think we haven't talked, I mean, the only types we have seen so far is ints, bool, and functions. So another sort of built-in type is characters, and character literals in Haskell are written with single quotes. So for example, this, if I ask for the type of that, it's of type character. And that's Unicode characters. So, I mean, I'm German, so we have funny letters. So, for example, this is also an umlaut, a U with 2 dots on top. It's on my German keyboard. So that's also a valid character. So it's not just ASCII. And there are like 20,000 or whatever. I mean, also all sorts of emojis. Right, so that's another interesting type. And Haskell also has strings. So for example, I can ask for the type of Kenya. Strings are written with double quotes. But it turns out that strings are actually in Haskell implemented as lists of characters. So this is another piece of syntactic sugar with these double quotes and writing it like that. So if I just type Kenya like this, I get this string, but I can also do K colon, so N colon Y colon A colon empty list, and I get exactly the same result. And I would also get exactly the same result if I do it like this. So all these things are the same. So in Haskell, a string is just a list of characters, which is one additional reason why lists are so important in Haskell, because strings are obviously important in programming. You often need to manipulate strings. So that means every function you learn that manipulates lists or works on lists automatically then also works on strings, because strings are just special lists of characters, which is very nice. But I mean, on the other hand, strings are not very efficient in Haskell, so there's a lot of memory overhead to storing these strings, these lists of characters. So in a later lecture, we'll talk about alternatives. So there are other textual types in Haskell libraries that are much more compact. So if you really do like processing large amounts of text, then string is probably not the best choice. But for small things like Kenya or so, it's perfectly fine. And it's very nice because it, as I said, all the functions that work on lists in particular work on strings, because strings are lists of characters. Let me see. So this I showed you. So actually string is just a type synonym. So I mean, we saw here Kenya, when I ask for the type, it gives me string, but it's the same as somewhere it's just type string is defined as list of characters. So I could, wherever I say string, I could just as well say list of character. Right, and we had the length of our, we defined this chain length function. There's also a function provided that's just called length. For example, I can ask for length of Kenya and I get 5. I can also ask for length of 34. I get 3. So that length function works for arbitrary lists. If I ask for the type of length, we see something weird. So we would have expected that length goes from list of A's to int. But actually there's type class we don't know yet, foldable. And what that, I mean, we talk about that in more detail later, but it basically means that length is not only defined for list, but for container types. And this foldable sort of means that T is a container type. So you can read that as if you have a container containing A's, then length tells you how many A's are in the container. And list is just a special case of containers. There are other containers. Right? So in particular now, I mean, length works on lists, on arbitrary lists. So in particular on lists that contain integers and on lists that contain characters, which are strings. So therefore, by having this function defined for arbitrary containers, in particular works on strings. So that's one of the advantages of, I mean, this is for some people, or for most people, probably very abstract and looks very scary in the beginning, but it has a lot of advantages. I mean, we have one length function that works for arbitrary containers with arbitrary elements in it. So you only have to learn this function once and the name length. And then it works for all sorts of things where it makes sense to talk about the number of elements. You don't have to use learn a new name for length of string and length of list and length of array and length of this and length of that. You have one length function, and the same function works for all these cases. So that's nice. Right. So of course there's more you can do with lists. For example, there is the element function, and it's not even only for lists, it's for arbitrary containers again. If you can compare element type for equality. So we have seen this before. We haven't seen this syntax. That's if you have more than one constraint. So before we had one constraint like A. Now we have two, and if you have more than one, you must put them in parentheses before this double arrow. So this means if you have a container type T and can compare the element type A for equality, then you have this elem function. And of course, this elem function given an A and a container of A's tells you whether that A is contained in the container. And it intuitively makes sense that you need to compare elements for equality, because how we want to check whether an element is in the container if you can't see, if you have an element from the container, you must somehow compare it to the given one. So we can try this out. So for example, strings. So we can ask elem k, elem k Kenya, and we get true. If I change it, for example, to a lowercase k, we get false. If I change it to a y, we get true again. And remember, just as a reminder, it's not very important, but last time I told you that functions, functions and operators are more the same thing. So you can freely, only that functions are always in prefix notation before the arguments, and operators come between the arguments in infix notation. But I also told you that you can convert one to the other. So if you have plus, if you have 3 plus 7, I can just as well pull the plus in front to prefix if I put parentheses around it. And I also told you that the same is true for functions. So normally they are prefix, but if I want to use them infix, I can put backticks around it. So if we tweak this again, I can instead move this between these two arguments if I put backticks around the elem, and it gives the same result. And I'm mentioning that here because normally you would ask, why would anybody do this? It's longer. You have these weird backticks, and why would you? But this is actually a common case where people actually do this because, from mathematics, maybe you know this notation that an element is, something is an element of a set. So this sort of more natural than putting the function name in front, to put it in the middle in this case. But it's mostly a matter of taste, and as you see, both work. Haskell is anyway, a lot is a matter of taste. So it's not one of these languages where there's only one right way to do it. It's rather the opposite. And everybody must find personal style. Okay, what else do we have? Again, you don't have to remember all of this, and you don't have to understand all of it. It's more an overview. So we also have any. So given a container type and a predicate on elements, it checks whether there is an element in the container that satisfies the predicate. We had our has block property, has block function on chains is very similar to that, but specialized to chains. So, for example, we can ask any even. And we get true because there are even numbers in the list, namely 2 and 4. But if I change those, then I get false. The same, I could, for example, ask any equals y Kenya. And here we also see that any, you could implement elem in terms of any. I just basically did. So instead of saying elem something, something, I can say any equals that something. Right. Here we see that, this is very abstract, defined for arbitrary containers, but you can, of course, specialize it to lists. As in the examples now, because at the moment, lists are the only containers we know. So I have to use lists as examples. So you can specialize it to lists. Same for any. There are other functions on lists. So for example, reverse, as the name suggests, reverses a list. Then plus plus concatenates two lists. So for example, Cardano blockchain concatenates the two strings. Filter only keeps the elements of a list that have a given property. So if I go back to, let's say, this list, let's so if I, for example, say filter even, it will only keep the even elements of this list. If I say filter odd, it will only keep the odd elements. You're probably wondering why I always do this : int. We'll come to that later. But basically the reason is that if I just write 2 and ask for the type, it doesn't say int, it says something weird. Basically what that means is 2 is an element of or value of any type which is numeric. So 2 can be an int, but 2 can also be a double or a float or some other word or byte. And therefore, in order not to confuse the compiler, I always the so-called type annotation to say, when I write 1 here, I'm actually talking about ints and not no other numeric type. And then you might wonder why I don't have to do that for the other elements in the list, just for the first. The reason is because Haskell has type inference and lists are homogeneous. So Haskell knows, okay, if the first element is an int, then all the other elements must also be ints, because all the elements in the list are of the same type. Haskell also doesn't have implicit coercion like in some languages like JavaScript or so. So if something, if an int is expected, a float won't do. So you must always, if you have two different numeric types, you must explicitly convert between them. But we'll have a whole lecture or part of a lecture about numeric types. So I just wanted to explain why I always have to do this. Because if I just write 1, 2, 3, then I get this annoying warning that he doesn't know what type that's supposed to be, and he defaults it to integer. You can also somehow switch off that warning with this here, I suppose. So I could say warning no type defaults, but so be it. So I prefer to give explicit annotations. Oh yeah, and map. So map is also these days well known in other programming languages. So it applies a given function to every element in the map. So for example, I can we haven't talked about import yet, so I can import other modules. Was there a question?
Yes. Adrian?
Yes, I got a question. What is the complexity that we have in the concat operation? Because we have immutable data structures, and I don't know what is the time complexity.
It's linear in the length of the left operand. And we will have a lecture about this immutable data structures later. So the point is that Haskell needs to do less work than you would think. So it doesn't always have to like copy everything. It can share because it's immutable. It doesn't need to create a copy, a clone. It can basically reuse part of the old structure in many cases. So it's often much more efficient than you would think. And concatenation in particular is as I said, linear in the length of the left argument.
Oh, okay. Thank you.
Welcome. I mean, we haven't talked about modules yet, so I can import different modules. I mean, as you see, some of these things, I should mention that. I mean, this any, for example, that I showed you examples and I didn't have to do anything and it was immediately available. So the reason is there's a special module, the so-called Prelude in Haskell that you can actually look up. So maybe I should do that. So if I just Google Prelude Haskell, then I end on Hackage. Hackage is I mean, we'll also talk about that later in detail, but Hackage is basically the standard Haskell package repository where people can upload their, packages. And I mean, these days there are tens of thousands probably of packages. So everything you can possibly think of is there. I mean, when I started with Haskell, that was one of the painful things, that there weren't enough libraries. So you had to do a lot of things yourself. But these, there's everything. I mean, there's web servers, there's graphics, there's whatever, JSON handling, XML, music, sound, robotics, whatever, mathematics, physics. So there's a library for everything. But I mean, wasn't always thus. But anyway, there's a library called Base. That is special because it's sort of packaged with the compiler. So whenever you install GHC, you automatically have the so-called base libraries. And in the base libraries, somewhere, all right. And in the base libraries, there is a special module called Prelude. And this Prelude is always by default imported automatically. So everything that's in this Prelude is automatically available if you don't do any. I mean, you can prevent that if you insist. And when we come to Plutus DApps later, there will actually be a good reason to exclude the Prelude. But for normal Haskell development, you don't. And then you always have this stuff in here, which is, I mean, quite a lot, but also not that much. So this is always available by default. So and these things I showed you until now, filter, for example, is in the Prelude. But there are others that are in the base library that are not in the Prelude. And if you want access to those, you have to explicitly import them. And I just want to have more examples. Import the module called data.character, because that has a function called toLower, which, as the name suggests, converts a character. Sorry, yeah, it does. I mean, it doesn't do anything to a lowercase character, but an uppercase character is converted to lowercase. Right, and there's also obviously to upper. Right, and I wanted to, so the map function, so for example, I can map the to upper function over the list Kenya. So that will now create a new list where it applies the given function, in this case to upper, to all elements of the list. So what that means is it will turn this word into uppercase, all uppercase. If I do to lower, then it turns into lowercase. There's also, I mean, we will see that later, but I personally prefer this notation. So there's also an operator for that. But anyway, so this is a very common function. And then two other, let me just see. Okay. These two also built-in functions. So it is the function, the identity function. It doesn't change anything. So if I do it Kenya, just Kenya, and that's completely polymorphic. It works on arbitrary types. And const takes two arguments, one of type A, one of type B, again, completely arbitrary types. But then it completely ignores the second argument and just returns the first one. So if I do whatever, const Kenya 47, it just returns Kenya. So it ignores the second argument completely and always returns the first one. That's why it's called const, because the value of this function const is constantly this argument. Then we have the usual you would expect. So this num, as I said, we will talk about numeric classes in more detail, but num is basically the superclass of all numeric types. So every numeric type you can plus add. So if I have 3 of type int plus 4 at 7, and the type of that is then again an int. But I can also, for example, take 3.5 of type double. So this is now a double precision floating point. And now actually the 4 here is also interpreted as a double. That's what I said earlier. These literals are basically overloaded. So they can be of any numeric type. And plus addition expects both arguments of the same type. So I say this is double, so the 4 must also be double. And then the result, this 7.5, is also double. Right, and we also have division, but this is not for arbitrary numeric types, only for fractional types. So for example, int is not a fractional type. So for int, I can't do this. If I try to divide 3 by 2, I get a type error that int is not fractional. If I instead try it for doubles, then it works and I get 1.5. Of course, there's also integer division in Haskell, but it's just not using this slash. If you want integer division, that's, you want integer division, it's called diff. So that's basically forgets the fractional part and just gives you the integral part back. Okay, and there's also another class similar to equality where you can compare types for elements, whether they're equal. There's one class called odd, and you can compare them by size. So for example, I can say 3 int less than or equal 7. That's true, but it's not less than or equal 2, but it is less than or equal 3. And of course, there are also the other comparison operators that you would expect. Finally, there's show. We haven't used show explicitly yet, but we right in the beginning of the when I started typing code in the editor, I added this mysterious deriving show. So the REPL is using show to display results. So if I type something like I don't know, plus function from int to int to int, if I now press enter, I get an error. It says, I mean, this is a perfectly valid Haskell value. It's addition. And I mean, I could, for example, apply it to 5 and 7, and I get 12. So there's nothing wrong with this expression. But in the REPL, if I just enter it like this, then the REPL complains it doesn't know how to display this to me. So the REPL uses the show instance. So show is the class of types that can be represented as a string. So if I ask for information on show, ignore all of this. So we talk about class data, but there's a show function taking element of this type and converting it to a string. So for example, I can do show 42, and I get the string 42, so 2 characters, 4 and 2 digits, 4 and 2. I can also show like a string, or like a character. So this is the string, length 3, a single quote, okay, another single quote. I can go Kenya. So this is, it escapes it here, so that would be double quote, then the letters for Kenya, and then another double quote. So that's often important, especially for debugging or for working in the REPL if you want to look at statements. There are other languages that display everything, and they just give you some weird pointer address if they from a lot of types. But Haskell is like that; it just refuses to show you something if it's not an instance of the show class. And this, we talk about, and we will see examples of all of this later. But this is just some of the most important type classes. So eq to compare for equality, odd to compare by size, num for numeric types, fractional for numeric types that you can divide by each other, show for types that have a display, a string representation, so you can show them in the REPL in particular. Read is the opposite, so you can parse. So if you want keyboard inputs, for example, to read an int from the keyboard, you can do this because int is an instance of the read class and knows how to parse string to a number. Enum is types that are enumerated, so basically just a enumeration of finitely many things. So a typical example is bool. Bool only has these 2 values, true and false, so that's element of the enum class. But it doesn't have to be finitely, it's or integers also. It basically means you can list them one after the other. They come in a well-defined order. Bounded means the smallest and the largest value, and foldable we saw is for container types. So you don't have to remember any of that. It's just that you have seen this already. And I think we should, let's do this last slide and then we can have a break. So normally, I mean, as I said before, this is like classes are like instances in other, interfaces in other programming languages. So, and normally you have to implement them. I mean, if you define a new type like our chain type, and I want to make it an instance of whatever the eq class, I would normally have to explicitly write code to do this. But luckily for some classes, so in particular for, I think, most, not all of them, not the numeric ones, but most of them here on this slide, you can do that automatically by using this so-called deriving clause. So I did that for show. So I didn't have to write any code for show. I just could use this deriving. So the compiler automatically implements this. That same works for eq and for ord. So if I can demonstrate if I, now I, for example, can say, let's say, Genesis block true equals Genesis block false, and I get false. So it can automatically derive that, and I could also compare it for, I mean, this is of course not so clear why this should be true. No, that is clear because they're equal. Sorry. If I do false here, so it somehow defines an order on these things automatically. Right, but if I try foldable, then it refuses. But there's a so-called extension. My editor, I can do that with one click. So if I on top of my module write this cryptic string, so this is so-called pragma, compiler pragma. So it's these curly brackets minus, I don't know why this annoying stars are there. Anyway, hash and then language and then the name of the extension. As you will see over the length of the course, there are a lot of extensions. So we are using GHD. We'll talk about the history of Haskell a bit later today. The GHD Haskell compiler, and that has a lot of extensions. So it's a lot of things that go beyond the Haskell standard. And I mean, right now, until now, we haven't used any. So this is the first time we are using one. So there is an extension called derive foldable, and then it can automatically derive the foldable class. And there are other, I mean, there are a lot of extensions in Haskell. And it's actually quite funny. I mean, the more advanced you get, I mean, when we come to more advanced topics, the list of extensions we use gets longer and longer and longer. So sometimes it's a bit ridiculous. It's like pages, or not like half a page of extensions. But anyway, we try to not go overboard with that. But now if we have foldables, now, for example, we wouldn't even have needed to implement our chain length function by hand, because now that we made it an instance of foldable, the length function is just defined. So we can just ask for the length of chain 2, for example, and we get the right answer. Of course, this is the advantage, as I said, to write functions polymorphically, because then as soon as your type is an instance of, for example, foldable, then all the functions available for foldable automatically exists. Same this has block. I mean, this is just also not needed anymore, because now we have any available for, sorry, not has block, the has block prop. So now using any, this is redundant. So basically you can avoid writing a lot of code by realizing that the types you are working with are instances of certain classes, and then if there are a lot of functions often available for those classes already, so you don't have to write them yourself. Okay, I think this is a good time to stop and have a break, except if there are any questions right now.
Yeah, so there are no questions, but I wanted to do a couple of remarks of things that people talk on the chat.
Of course.
So you won't see the repository of the assignment in your GitHub, because it's part of the course's organization. So the only way for you to access the repository is to actually like click on the link, and you will see the URL that Lars showed a bit ago. and you have to clone that address, and that's it. Or just click on the online repository and to get it open. If you already accepted it, it's okay. You can keep clicking. It's just going to show you the one that you already created the first time. So that's how you can continuously accept. Once you clone it, that's it. It's on your computer. But if you like forgot to clone it the first time you accepted it or whatever, you can just click again, and so it's going to tell you it's already created. You can see it here. That's one thing. And the other thing is that Lars had to use the local environment because Stylish Haskell, this formatter, wasn't available. And that was because there was a small error in a path in the configuration of VS Code. So all you have to do is to change the configuration of VS Code to point to the binary, and you will have the formatting. Of course, for the ones that already created the first assignment, you have to do it manually because the repositories has already been created. But we can show how to do that once Lars comes back. And for subsequent assignments, it's going to be already like correctly formatted. So that won't be an issue anymore. If anyone has any other questions about this aspect. Okay. Okay, so let's take a break.
Yes, maybe, I don't know. It's for now, maybe 15 minutes until
Yeah.
40.
Okay.
Okay.
Sure.
Okay. Talk to you in 15 minutes. Okay. Should we continue? Are there any questions? Okay, if there are no questions, then let me share my screen again. So what we've seen until now is maybe, I mean, somewhat unusual for people coming from more traditional programming languages. But I mean, these days, TypeScript or Java, or those languages also have a lot of the things we talked about, like this fill and map function, for example, is quite common. But now when we come to explicit effects, that's something that's really unusual for Haskell and even other functional languages, like OCaml, for example, don't have that. So that is one of the things that really make Haskell somewhat strange or really unusual for people that see it for the first time. So what's very important, I mean, is the concept of pure functions, and the idea of a pure function is a function where the result only depends on the input and they have no side effects. So that's basically the idea of a mathematical function. You put the same input in, you get the same output. And that may seem or sound obvious, but in other programming languages, it's not the case, not necessarily. So for example, in TypeScript, you can write a function that takes an int and returns an int. But in the body of the function, you do some sort of network call and ask some server for another int and then add it to the given one or so. So depending on what the server tells you, if you call this function twice with the same input, you can very well get different outputs. So that's not a pure function. So in most programming languages, pure functions are rare. At least you can't see from the type signature whether a function is pure or not. In Haskell, things like that are not allowed. So side effects are not allowed. A function from int to int guarantees you that when you put the same, if in Haskell you have a function like f from int to int, if you put the same int in, you will always get the same int out. Of course, if that was all you could do, then the programming language would be quite useless if it has no way to interact with the outside world. So of course, in Haskell, there is the option to have functions that do have side effects, but the point is that you can see that at the signature. So the type system guarantees that a function like this will never have side effects. And if you want a side effect, there is this IO out of the type. So we have a full lecture on IO later, but this basically means G is a function that, given an int, will eventually produce an int, but it can possibly do side effects. So in particular, it's not guaranteed that the result will always be the same int. So for example, the function to read a file from disk, Haskell is in the standard library, it's called read file. And file path is just a synonym for string. So given the path of a file, it returns the content of the file, but in IO, so with side effects. So you can, of course, if you call that twice for the same path, you can get different results, because between calling it the first time and calling it the second time, somebody could have edited the file. That, I mean, can actually, sorry about that. We can actually try that in the REPL as well. So let me see. What files do I have lying around? So for example, this HiYAML would do, or this overview Haskell Cabal. So for example, I can do a read file in the REPL Cabal. I get this result. I mean, it's not formatted nicely, but it's the content of this file. But I mean, of course, if I change this to I don't know, J, and save, and call this again, then I get a different result the second time. Let me change that again, otherwise problem. Anyway, so, but this is only possible because the type of, the type of read file has this IO there. If the IO wasn't there, it would be guaranteed that each time I call this function with the same arguments, I also get the same results. So for example, to compute the length of a file given the path, I can't do this because length expects a container, something like a list or a string, but read file is not a list or a string. It's an IO list, an IO string. So this just won't compile. So if I ask for the type of length read file this, I just get here an error that IO is not foldable. So IO is not a container type. So I can't do it like this. Obviously, in Haskell, you can compute the length of a file, just not like this. So this, without understanding why this works, actually will be correct. So this is now a side affecting function that gives me an int. So I can do this and I see, okay, this is now 406 bytes long. If I edit the file here and add one and call it again, I get 407. But we see that this IO is somehow infectious. So I had this read file, which was IO string, and now to get the length of a string, I have something of type IO int. So basically, once you have an IO somewhere, you can never get rid of it again. So everything is contaminated with this IO marker, the side effect marker. And I think I will skip this. So there are ways to use like atomic simple IO actions to get more. So this is what we just used. So given a function from A to B and an IOA, you can turn it into an IOB. So in our case, this was length. So A was string, B was int. And we had our read file, which was an IO string. So with this operator, we could length this operator, this read file, it gave us an IO int. This one concatenates two actions. So you first do this, and then you do that, and you give the result of the second, forget the result of the first. This basically, it's a, I mean, I think I just skipped that. And this is sort of, as we will see, the most powerful one. So the side affecting action returns an A, and the way to turn A into another side effecting action that returns an B gives you a B. So what this will do is it will perform these side effects, get an A, apply this function, get an IOB, perform those side effects, and then get a B in the result. But as I said, there will be a whole lecture about this stuff. The point is that you can construct complex IO actions from simpler ones. But as I said, this IO, you don't get rid of it again. So once something has side effects, then everything you do with it also has side effects. And you can always see that at the signatures from the types. And we cannot lie about it. The compiler prevents us from lying about it. The compiler checks that. So we can't say a function doesn't have side effects if it actually has side effects. So we can't just leave the IO out, which is not 100% true. So there are escape hatches. So you can actually lie about it, but this is only for like very specialized use cases. And normally you never do this. And I mean, functions that have an IO in their type are called effectful programs. So they have stronger requirements than non-effectful ones. And that leads naturally to a programming style, excuse me, where you try to push the side effects to the edges of your program. So most of your code ideally is pure, just uses pure functions, no IO. And then only at the periphery of your function, I mean, when you need to get user input or when you want to produce output, you involve I/O, but the business logic and the bunch of code, the majority of your code is normally or ideally not using I/O and just using pure functions. It makes it also much easier to test. For example, if you have a pure function, because a pure function means same input, same output. If you have checked it for input, for this input it will always work because it will always give the same result, which is not true for other languages. So it's much easier to test pure functions. Right. So this is an important topic. That's maybe the most striking thing that makes Haskell different to other languages, these explicit effects. Arguably also the most important feature of Haskell. That makes it stand apart. Another famous feature of Haskell is so-called lazy evaluation. But one could argue that that is more the historical thing. And even if Haskell was not lazy, it would still be Haskell. Whereas if you take the explicit effects away from Haskell, it wouldn't be Haskell anymore. So just to have an example, until now we have constructed our chains by hand. So they were all quite short because I didn't want to type so much. But now let's write this builder function. So build. So the idea is, given an int, I want to construct a chain with int payload, and the length of the chain should be this given int, which allows me to build long chains. So given integer n, so now some syntax we haven't seen yet, I can basically make a case distinction. I can say n, I first write it and I explain it. Let me just write it and then explain it. Build n minus 1. Oh, sorry. Yeah, block. Okay. So this syntax, we haven't seen that yet, this vertical bar. So there can be a Boolean after the vertical bar. And then when the compiler, or the Haskell runtime looks for a matching equation. So as I said last time, always starts at the first equation. And if that fits, it uses it. Otherwise, it goes to the next. So here it also starts. And then in this case, it will evaluate this Boolean condition. If it's true, it will use this right-hand side, and if not, it will try the next branch, or maybe also the next equation is there, if there is one. Otherwise, it's just a synonym for true. So I could just, if I have written true, it's just used because it reads nicer. So you can read that as build n. If n is less than or equal 0, it's just the Genesis block. Otherwise, it recursively calls build itself and adds this payload n. We can try this out. So if we do build 0, I must reload. So if we do build 0, just the Genesis block, build 1, it's the Genesis block and payload 1 added, build 2, like this, with 3. And of course, I can also do build 100, for example. So I can quickly add, get very long chains. And now I think, so let's, for example, do the length of build 10 million. Now we have to wait a bit. So a couple of seconds. Actually, there is something, but I always forget what it is. Is it, just a second, I always forget. You can get timing information. Plus S. So I can say Z plus S. Now I can call this again. And it tells me how much memory it used and also how long it took. So 6.33 seconds. Now, if I do this, I think on the slides they use this has block prop, which of course is exactly the same as any, but let's use it as block prop even. Again, 10 million. And it takes virtually no time whatsoever, which is surprising if you come from a traditional programming language, because it shouldn't really make much of a difference. I mean, in a traditional programming language, in both cases, you first need to construct this list of 10 million elements, chain, I should say, 10 million elements, which takes a while, and then you can compute the length or check whether there's an even element. So it's not obvious, or it may be surprising why this takes so much longer than this. And this is because Haskell uses so-called lazy evaluation, which roughly speaking means it only evaluates what it needs to evaluate. So we can now on the slides, check how that's evaluated, or how one could evaluate it. I mean, we saw last time how Haskell evaluates things, that it just substitutes definitions. So we have these equations that define our functions and values, and it just plugs them in. So, for example, we can plug in the build million, the definition of build. So this is just, instead of build 10 million, we inline basically the definition. And then we can evaluate this, for example. So 10 million less than or equal 0 is false. So if we simplify this further, I mean, I think we haven't seen if then else yet, but it does the obvious thing. So it takes a Boolean condition and then branch and else branch. If this is true, it takes the first, otherwise it takes the second. I mean, we defined it slightly differently with these vertical bars, but it's basically the same thing. So because this is false, it will take the else. So this is replaced with this. And now we can evaluate this. And so now we have done basically one step, and we end up with almost the same thing, has block prop even, but now the argument, it was build of 10 million, and now it's this. And we have a build of 9,999,999. And now we could, of course, do the same thing again. And then it would take forever, or a long time. Because we would need to do this 10 million times until finally we get to this Genesis block. And then we have to basically substitute everything back until finally we have computed this chain. And then we can worry about the definition of even and has block prop. So that's basically what would work in other programming languages. And that's why in other programming languages, this would take a long time to compute. Haskell, however, is free to, I mean, you could also evaluate other things first. Instead of evaluating this here first, you can do one of the other things. And Haskell has the rule, it starts with the leftmost outermost, which in this case means it will not evaluate this. It will first evaluate this has block prop. So if we do that, so we substitute the definition for has block prop. That had two cases for the Genesis block and the other case, so we don't have the Genesis block. So instead we have this, or rather, I think there's a step missing here. Sorry. Right. Sorry, no, there's no step missing. So if we, I mean, I'm just saying, so let's say we did this first. So now we have this block constructor here. And so we know in the has block prop property, let me show you that again. Here there were two equations, one for the Genesis block constructor, one for the block constructor. So now we know this one applies because we have reduced it to this where we have the block constructor here. So now we can substitute this definition in case of has block prop So when we do that, we get to this. And now we can evaluate this first, if we want. And this is true. So this is an even number. And we have this thing here still left. But from the definition of disjunction of logical OR, we also know that true or something is always true. So without needing to know what this expression here actually is, we know the result is true. So the point is we don't have to evaluate this further. I mean, now for 9,999,999, then for 9,999,998, and so on. We don't have to care what this is. We don't care whether it's true or false, because we already know this is true, so true or anything is true. And basically the evaluation order in Haskell is different than other languages. So if you apply a function to arguments, f of x, or f of x, y, let's say f of x, then in other languages, they use something called eager evaluation. You always first evaluate the function argument. So if you want to compute function f applied to an argument x, then in other languages, you first evaluate the x, and then you evaluate the function. Haskell does it the other way around, so it goes from outer to inner. And that has the effect that sometimes, like in this example, it doesn't need to evaluate everything because it already knows the answer without need to evaluate further. That's why it's called lazy evaluation. It only evaluates what it needs to evaluate in order to give you the answer. So in this case, it only needs to evaluate this one step. Then it already finds an even number, and it can immediately stop without ever having to look at this rest. And that even works for infinite things. So that's why it's possible in Haskell to basically work with infinite structures. I mean, with this build, we can't do this, but I can define something very similar. I can say, for example, infinite chain, and I just define it as block, yeah, for example, like this, or 42 is nicer. Infinite chain, let's say it's also a chain int. This is a perfectly acceptable definition in Haskell, even though it's obviously an infinite loop, right? It calls itself. So if I try to print it, I mean, if I reload, if I try to print this now, it will just loop forever. I have to press Control C to interrupt it. But if I do has block prop even infinite chain, it immediately tells me yes, true. For the same reason as in the example we saw on the slides. It doesn't need to evaluate this infinite thing because it immediately in the first step finds the first 42. 42 is even, so it can stop. So it's possible to work with basically infinite structures in Haskell because of laziness. Of course, you can, I mean, all programming languages, or I mean, all like general purpose programming languages are Turing complete. So obviously you can somehow achieve the same in other languages as well, but you have to really work for it. Haskell, that's the default behavior, this laziness. So some things are really neat in Haskell. For example, a common pattern in solving problems is you are looking for some sort of optimal or feasible solution to a problem. And sometimes it's easy to come up with all possible solutions. So you can often split your problem into two parts, one that generates potential solutions, and then one that takes these potential solutions and checks them somehow, whether they are admissible or whatever. And then basically stop once it finds a good solution, whatever that means. And in Haskell, this part that generates the solution can potentially generate infinitely many solutions. So you can just generate the list of, I mean, the infinite list of solutions, and then just filter it for good solutions, take the first good solution, and that will work in Haskell. Because it never has to evaluate this infinite list. It only evaluates it as far as it has to make progress. So that's very neat and often very useful. I mean, as I said, you can, of course, somehow achieve the same in other languages, but it's much more involved. I mean, you can't generate everything in one go. You have to like generate a piece and then check and then generate again. So in Haskell, I mean, laziness makes a lot of things much nicer, and it's very cool if you have never seen it. So we can work with potentially infinite values, and it allows for better separation of concerns and definition of control flow structures. So we will see that later, what's meant by that control flow structures. But the separation of concern is an example would be what I just said, this generate and test. So in Haskell, you can basically write one function that gives you the infinite list of all possible solutions and another function that checks the solution, whether it's good or not. And then you can slap the two together and say, okay, I just look for the first element in my list that passes the check. And it doesn't matter that the list is infinite, it will just start searching, keep searching until it finds a good solution and then stop. And it won't have to first compute infinitely many other potential solutions. So you can write these two parts separately, the generator and the checker, and then put them together and it just works. If you want to do that in another programming language, somehow they have to be interleaved. So you generate a potential solution, check it. Then you call the generator again to get the next potential solution and check it, and so on. So that's meant by the separation of concerns. So it makes many things have a very elegant and nice solution in Haskell. It does, however, also have disadvantages. So it becomes difficult sometimes to ask about performance, because it's never clear in which order things are evaluated in Haskell programs. So it's not like step by step from top to bottom, left to right. So because of this lazy evaluation, you never know when a given expression, a given line of code will actually be evaluated, if at all. Maybe it may never be evaluated because it may never be needed to give you the answer, or it may be. So in order to estimate performance of a program, it's more involved, because you don't know. I mean, with other languages, you know exactly everything will be evaluated, everything will be executed. With Haskell, not, so it makes it more complicated. But it's also very cool and almost like magic if you've never seen it before. But as I also said, so people argue that it was a wise decision to make Haskell lazy or not. So I think it was like in fashion back when Haskell was designed to experiment with lazy languages. So it's more like a historic thing. So, and if Haskell was not lazy but strict, that would not really change, I mean, not dramatically change the character of the language. Okay. So that's almost the end of this introduction. So we have higher order functions, and it's easy to define them in Haskell, but that's something that's common for functional languages in general. And polymorphism, as I said, is also like all modern languages have that these days, can define new data types in other languages. Pattern matching is also sort of becoming more common, especially in statically typed functional languages. Type classes are quite unique concept in Haskell, but they are very similar to, as I mentioned before, interfaces, for example, in other languages. So that's also not really. But this explicit effects and the lazy evaluation make Haskell truly special. And I mean, there are other languages go even further than Haskell, have an even more advanced type system, but they are even less, I mean, they are more like research languages, whereas, I mean, not really used in production. So especially these two things are really unusual. So if you are used to programming in another programming language, it will take some time until you get used to this. Right. And I mean, you already started with the exercises, hopefully, yesterday. Right. So that's the first I mean, this introductory lecture done. So we still have some time. So I think I definitely have to start with the next lecture, which will now take a much slower pace and go back to defining functions with these different equations and so on. this so-called standard design pattern for functions. But first, if there are any questions, feel free to ask.
No questions so far. Yeah.
Okay. Okay, then let me close this. Let me see. So that was 2. There's 3. Okay, and let me just comment everything. I always find it better to do this live. Okay, and let me find the slides. And then, so let's just see how far we get today. We certainly won't finish with the whole lecture. So the goal is to introduce some very common types in Haskell. So bool, we have already seen. Lists, we have already seen. But we'll also talk about maybe and binary trees and some other types. And most importantly, talk about the standard design pattern for functions. And there's also a fancy Greek word for it, katamorphism. So we'll look at a lot of examples for all of those types until it gets really boring, because this is like, it must become second nature for every Haskell program, this standard design pattern. I don't know, I thought there were slides somehow about the history of Haskell. Maybe I skipped that out. Or anyway, maybe I should just say a couple of words that, I mean, I'm never very good with these dates, but I think it was like in the late 1980s. I mean, first of all, it was designed by committee. So normally that's always a red flag. I mean, normally the languages that are made by one person are much more successful, like Python or C++, Ruby. But in this case, somehow that was an exception to the rule. So even it was a committee that designed Haskell. I mean, it was very, was successful. And it was first, I think, back in the days in the 1980s, universities were interested in functional programming, but basically every university had their own implementation. So they all had their toy functional languages, and then they wrote research papers for their own language. And that, of course, made it difficult. I mean, every university had to basically do it for themselves, and they couldn't really collaborate, and they couldn't really build like libraries or stuff because everybody was using their own language. So at some point, then they decided to design a common language, like a research language that everybody interested in functional language research could use, so that people could share their programs and so on. And that's how Haskell was created. So it's somehow inspired by prior, like ML and Panda, I think. Anyway, because back then laziness was in fashion, Haskell became lazy. And I think the first official standard of the language is from 1998. And since then, there's been one more in 2010. And right now there is something, is there 2021 or I forget? But there's like quite recently sort of a standard. And then it was a like specified language. And in the beginning, there were also several implementations of this language, different compilers. And I mean, when I first started, I have been doing Haskell for almost 25 years now, more than 20 years, definitely. And when I started, there were certainly different compilers, GHC, but there were also, I even forgot the name, but there was another one. And I actually used the other one because it somehow felt easier to install and so on. But somehow, by now, all the other compilers have died out and are not supported anymore, and everybody uses a GHC compiler, which either stands for Glasgow Haskell compiler because it was developed at the University of Glasgow, or for the glorious Haskell compiler. That's, I think, more of a joke, this glorious thing. And because, I mean, these days, basically, Haskell and GHC is almost synonym. So nobody does other compilers anymore, and everybody does GHC, which is sort of a bit of a bad situation because the language is more or less defined by GHC. So everything, I mean, Haskell is what GHC does. And there are all these extensions. So GHC was not, or the developers of GHC were not satisfied just implementing the language standard. They added all these extensions. And we'll talk about that later. And what else? I mean, when I started, it was still quite painful, and there were not libraries, and it was difficult to actually get it to work and set up the environment. And especially if you had like different projects with many dependencies, it was really painful to find like the right versions of dependencies that fit together and so on. But that has become much better over the recent years. So in the last 10 years or so, that has dramatically improved. So these days, normally it's actually quite pleasant and easy, and there's very good tooling. And as I said, there are libraries for everything. You can, whatever you want to do, web programming or databases or music or anything, text processing, you can do everything in Haskell these days. What did I want to say? Oh yeah, I mean, the second half of the course, when we come to Cardano, there the story is still a bit like in the old days, a bit. What used to be quite painful to get Plutus, for example, working, the smart contract language of Cardano, because I mean, our company IOG, basically all our software is written in Haskell, and we have written probably literally hundreds of packages and like different teams. So it was at times quite difficult to find the right dependencies to make everything work. But this is also much better recently because, I mean, I showed you Hackage before, this package repository. So basically IOG set up, you can have your own version of Hackage. So we did that. And that makes it much easier to find compatible versions. So these days, it's far less painful, especially with technologies like Nix or Docker and these dev containers and Git pods and whatnot. It's these days relatively easy. I mean, one click to give you, for example, an environment where everything just works and fits together, and you don't have to worry about that too much. Okay, but I mean, that's like a couple of weeks away. So let's start with basics. So Booleans. I mean, we have already seen that. So this is the definition. And it's also not built in. So very little is actually built into Haskell. So I think like ints and characters are built in. But Booleans, for example, are actually defined in the prelude or in one of the base libraries. And it's just another data type, no special treatment or syntactic sugar or anything like that. And just has two constructors, false and true. So you can construct the Boolean. I mean, the Boolean has two possible values, false or true. Okay, both of type bool, obviously. Okay, and if we want to define a function on Booleans to somewhere, there's some typo. It's supposed to be 3 dots. Then typically we would have one equation for the false case that tells us what the result of the function should be for false, and the second equation for true. And we mentioned that in the introductory lecture. So if you define a function, what's on the left-hand side of the equal sign is called a pattern. And right now, until now, I haven't formally said what that is. So there are several types of patterns. So one is a saturated constructor application to other patterns. So, if we, no, maybe not. So in this, saturated means the constructor and all its arguments. In this case of bool, false and true doesn't have any arguments. So the constructors themselves are patterns. So false is a pattern and true is a pattern. Alternatively, variables are patterns. So we have seen that before in the introduction, where we wrote something like block length, block C or so. The C was a variable, so that can match everything. It's like a wildcard, but it has a name. So then you can use the name on the right-hand side of the equation. We also briefly talked about underscores. So it's like a variable, but only if you're not interested in the value. So you don't bind it to a name, so you can't use the value on the right-hand side. And finally, literals. So your pattern is also something like 0 or 1 or 2, or character literals or string literals or list literals. That's basically already it. That's allowed what's on the left-hand side. And I also already explained that, that when it's evaluated, it starts at the first equation, so top to bottom. So it looks at the pattern and tries to match them. And as soon as it finds a matching pattern, it uses that equation and stops searching for more. So that means if you have a catch-all case, like just an underscore that matches everything, this must be the last equation. Because if it's the first, then the first equation would always match everything and the other equations will never be looked at. And so here the best practice is to, if you want to define a function on a data type, and the idea is to always, when you are stuck, you split the problem into cases for each possible constructor. Oh yeah, and one last thing for this matching. So if the cases do not overlap, then the order doesn't matter. So it doesn't matter which equation comes first if they are mutually exclusive. Like in our case, the two constructors, generalist block and block. I mean, a chain is either the one or the other. It can never be both. So they are not overlapping, and therefore it means we could have written all our examples the other way around, with the block case first and then the generalist block. Right. So for example, let's say we want to define the not function. And I mean, this is now like baby steps. So logical negation. This is, of course, already built in. Let me just write this quick. Just want to get an error. Okay, come on. Why don't I get an error? Let me just check quickly.
No, because you're not running it undefined.
No, I'm talking about the not. Shouldn't that clash with the prelude?
Right. Yes, it should.
Maybe there's no.
Maybe you can import the module into the REPL explicitly.
I thought. Okay, yeah, let's do that. Let me ask for the type of not. Okay. Okay, fine. I thought I would have gotten an error before, but anyway. So now if I ask for the type of not, I get an error that it's ambiguous because it could refer to the prelude not. So I talked about the prelude before, so the standard library that all gets imported. So there's not is defined, or this one. So it's not allowed in Haskell to have two different things with the same name that are both in scope. So in this case, I could either use, name my thing not prime or something. What I can also do is I can say import prelude. So, and then there's syntax we haven't seen before. Sorry, prelude hiding not. So that means don't import the not from the prelude to here. And then this clash should be avoided. So now I can, for the type of not, now it's fine. Okay. Undefined is another, it's also defined in the prelude. Undefined is defined in the prelude. So if you don't know what to write, you can basically write undefined. However, on the slides, they recommend to do instead an underscore. Underscore is always an error. It's a so-called hole. So if you don't know what to write, you can instead write an underscore, and that won't compile. But it will tell you what the type is that's expected there. So the compiler helps you, and I mean, if you use like Visual Studio, then just hovering over it, it says found hole underscore of type bool to bool. So, okay, it says, I mean, what you are supposed to write here. And in this case, of course, it's obvious. I mean, I just wrote there, but it can be very helpful if you're deep in some definition to know what type is expected. That's also called type-driven development. So you let the types guide you. So now if you want to define a function, it's often helpful to like explicitly name the arguments. So instead of doing it like this, you can say, for example, not b equals, sorry, not b equals this. Right now, if I hover, so b is now of type bool, and now the type of this hole has changed. Earlier, when I didn't have this b, the hole was bool to bool. Now, because I have not b, now I basically must just define what is the result of the function I'm defining, not apply to this Boolean b. So now I'm supposed to write a bool there, true or false. But of course, I don't have enough information to, I mean, I don't know what to write there, right? I mean, I want to negate, but because I don't know what b is, I don't know what to write there. I mean, the only thing I could write there right now would be b, but which would be wrong, because I don't want false to go to false and true to true. I have to negate. So in this case, I mean, if you go back to the slide, there was somehow the this tip here: split programming problems by expanding variables into all possible constructors for the type of the variable. So now I'm sort of stuck with my implementation. I don't know how to go on. So I can follow this tip. So I only have one variable, b. So the tip tells me to split my problem into all possible cases depending on the constructors of this variable. So the variable is of type bool. Bool has two constructors, true and false. So the tip in this special case says split my problem into two cases, one where b is false and one where b is true. So I do this now. I just copy this, and now I look at the special case where b is false and the special case where b is true. And I align, I mean, this is not necessary, but everybody does. I mean, it won't give you a compiler error if you don't, but it looks ugly. So people always align these equal signs. Okay, and now have I gained anything by doing that, except I needed to type more? Well, now, I mean, this hasn't changed, so I still need Booleans there, but now I have more information because now the b is gone and I have a specific value here. And I know what false logically negated is, namely true. So now I can remove the underscore and write the result there. That's true. And same negation of true is false. And I can compile and I can reload and I can try it. So not false, true, not true, false. So this is a very first example, very slowly, this so-called standard design pattern of functions. We see whether the slides have any more wisdom to okay, so that was that. Reflect, yes, we reflected, we tested, everything good. So now let's try something more ambitious. I mean, we have used that in the introduction lecture already, but let's say that was not provided in the prelude. So we have to define logical OR ourselves. Okay. So, I mean, if we first start with just like this, I mean, okay, fine. We have to define the function bool to bool to bool. So now what did we do here first? We gave names to the function arguments. So let's call it, I don't know, B and C. So we could do BC, for example. So B and C are now both type bool. Right, and now I need a bool here. But without knowing more about B or C, I'm stuck. I don't know what to write here. And by the way, I could also, this is again this thing that I mentioned at the beginning on Monday and also the beginning of this lecture. I can use prefix notation for an operator if I put it in parentheses. Alternatively, I could also use infix and then write it like this. Not here, though. In the signature, I must use the prefix notation. That's a matter of taste, what's now nicer. So maybe I should go back to prefix in this case. Doesn't matter. Right, so I'm stuck. So what did we do here next? So we split by constructor. So now we have a choice which one to split, B or C. Let's just do B because it comes first. So we duplicate this and we consider the special case where B is false and the special case where B is true. Right, let's look first at this at line 11 here. Because in this case, we don't care what C is. If the first argument is true, then we know the overall result is true. So we don't have to look at C, we just know the answer is true. So for this case, we are already done. Now there's this squiggle because we are not using the C on the right-hand side. So the editor recommends that we replace the C with an underscore, which makes it explicit that we don't care about the value. Okay, and what do we do in this case? I mean, we could be smart about it. I don't know what the slides do, but I mean, if we want to be mechanical, so the first is false, so we don't know. So we can just in principle do another split. So we could now split by C. We can use that false, false, and false, true. And now, I mean, we know what the results are. So false or false is false. And true or true is true. So this would be sort of a valid definition. However, if we look at this, I mean, remember the second argument was the C. So we notice false, false, true, true here. So we can actually go back, don't do the split, and immediately say C, which is shorter. And because of laziness, it also is more efficient because we don't have to evaluate the C in order to give the answer C. If we split, then we do have to evaluate C. But I think that we'll talk about that a bit more later, or maybe soon. Right, so this is a second example of using this process to define functions. So we can try this out, of course, as well. So true or false, true, true or true is true, false or true, true and false or false is false. So that seems to. Okay, let me see whether there's. Right. Okay, that's basically what I did. And of course, I mean, we could also, instead of writing in two equations like that, we could also be mindless and just spell out all four cases. So that would also be fine and correct. However, that's already what I alluded to. Let me just do this and call it, I don't know, maybe with 3 bars. So let me just copy this and define a variation with 3 bars, where here now spell everything out, all the 4 cases. Sorry. Right. So that should, I mean, it's a bit more to write, but it should behave the same. And if I do my examples here, if I now do that with 3 vertical bars, true, false, true, true, false, true, false, false, I get the same answer. So it looks as if this is more a matter of taste, which is better, and I can do both. However, that's not completely true. So let's take something like loop. I don't know whether that thing read my slides. I have no idea why Copilot knows that's on the slide. Brightening. Anyway, so this is, I mean, it's called loop because it loops. So it's just defined by itself. So, I mean, so if I do loop type int, for example, it will just it will just hang. So it now it's an infinite loop because it tries to evaluate loop. So it puts the definition of loop in, and therefore it's an infinite loop. So I have to press Control C to interrupt it. So now if I do true 3 bars loop, I don't get an answer, and it doesn't crash, but it hangs, which is maybe not surprising. However, if I do 2 bars, then it tells me true. It doesn't hang, and that's again due to laziness. So if we look at these two equations, so in this case here, it only looks at the first argument, and this equation tells us, okay, if the first argument is true, I don't care about the second one. The answer is true. So in that case, it will never try to evaluate loop. It will immediately respond with true. In this case, however, in order to decide which of the 4 equations to pick, it also has to evaluate the second argument. So it has to evaluate loop, and then it runs into this infinite loop, and it gets stuck. So that means even though for like the 4 obvious cases where both booleans are false or true, these definitions give the same result. They do not give the same result if one potentially of the arguments is an infinite loop. And of course, it doesn't have to be an infinite loop. You can also think of a computation that takes a very long time. So maybe instead of loop, it's a perfectly legal Boolean, but it has to evaluate millions of conditions to give an answer. So then if I use the triple bars here, it would take forever to evaluate. But here it would be instantaneously. So it does make a difference. So one should try to basically be as lazy as possible to, not split variables, pattern match on variables if you don't have to. If you can give the answer without looking at something, you shouldn't look at it. So that is good for laziness. Of course, we could also have like a 4th version. I don't know what to call that. 4 bars is a bit silly, but why not? The other way around. Probably should call it B. So instead of making the split on the first argument, I could just as well have made it on the second argument. And that would be completely correct. It would have the same advantage as this one, only now the roles of the 2 arguments type. I should also demonstrate here, if I do this, so this true loop gives me an answer. If I do loop true, it hangs. So it's not symmetric. Because of the way I wrote equations, I do the pattern match on the first argument. So if the first is a loop, I get stuck. If the second is a loop, it's fine. And now in this quadruple bar thing here, it's reversed. So now this worked fine for double bars. I have to reload. But now it hangs. But this one, which hangs for double bars, now suddenly works for these quadruple bars. And it's not that one is better or worse than the other. It's just whatever. I think in the Prelude, the version that we hit here, the built-in, not built-in, but like standard version is this one. But there's no convincing reason. It could just as well have been that one. I'm not sure whether there's now a slide about shortcutting. Right. I mean, we wrote this loop. There's also this undefined that I used before. If I ask for the type of loop, this is a weird type. It has a type of it's basically generic for it's simultaneously every possible type in Haskell. And that, I mean, if you think about it, that's sort of paradox. I mean, how can that be? How can something be an int, a string, and a Boolean, and all at the same time? And the answer is the only way it can be is if the computation never stops. So if it like crashes or gets stuck, that's why this type is possible. And I used this undefined briefly before. That's in the prelude. That has this, I wanted to say, has the same type. It has this weird constraint here, but I mean, in older versions of Haskell, it had exactly the same type. So I don't really need this loop thing. I can also use undefined, and undefined is somewhat nicer. So if I do this again, what I did before here, so instead of loop, write undefined, same behavior. It doesn't crash, it gives me the result. But the advantage of using undefined over loop is that with loop, we just get stuck. And with undefined, we immediately get an exception. And it gives us where the exception happened. So undefined is somewhat nicer because it has support from the compiler, sort of. So so normally people use undefined instead of something like loop. And there's also something more explicit, and that's called error. So that's a function actually. From string, remember, list of characters just string, to arbitrary types. So you can, basically it's the same as undefined, but where undefined always has the same error message, this prelude undefined, you can customize the error message. So I put, for example, here, I mean, this works. I can now also do error boom. It still works, but if I now switch it to see, now I get this boom, the string I picked here in the error message. So that's why I might want to use that. So that's quite useful, this undefined and this error. So undefined is often used during development if there are parts of your program. I mean, I said before on Monday, it's good practice to always permanently compile your program. It should always compile, because if you first write hundreds of lines of code and don't compile and then start compiling, then you normally end up with hundreds of errors, and then it's very painful to fix them. So it's much better practice to always keep it compiling. But of course, you can't really do that. I mean, you must start somewhere, and then there will always be holes in your code. I mean, things you haven't implemented yet. And the common practice is to, as implementation, use undefined, because undefined is any type. It can fit into every hole. Wherever a Haskell term is needed, you can always write undefined. And so then the compiler will be happy, and you can concentrate on the things that you actually need to develop or want to write first. And then over time, you remove the undefineds with actual implementations. And error is also useful. I mean, to indicate, I mean, to make it easier to find what happened. And as here's on the slide is also this remark that I made. All that I've been saying now is not only true for crashes or loops, but also for computations that take a long time. So of course, it's nicer if we can evaluate this logical OR, for example, if we don't have to do computation that takes forever, because we know the answer already from evaluating the first argument. And same if then else. Let me just see whether there's right. So we can define a function if then else from some Boolean and then an arbitrary type A. Again, I mean, if we want to follow this, or we can just define it like this. So if the Boolean is true, we take the first argument, the second argument, that's our result. And we ignore the third argument. And if the Boolean is false, then we ignore the third argument and like this. So we can define this function and it works as expected. So we can reload and say if, then else, whatever, 2 less than 4. Yes. No. Will give us yes. No. So that works, unsurprisingly. Okay. And now what about laziness? So if I, instead of no, write undefined, it doesn't crash. So the condition is true. It only evaluates this first branch, the yes. It doesn't look at the second one. However, if I now have a false condition, then that will crash. So it has this so-called shortcutting behavior. So if then else, if the Boolean is true, then only the first branch is looked at, and if the Boolean is false, only the second one is looked at, and this is not evaluated. And this is actually something you don't only find in Haskell or in lazy languages. That is a feature of many languages. I assume, for example, TypeScript also have that. If you have an if, then else, or Python. Then depending on whether the condition is true or false, only the then branch or the else branch is looked at. However, in Python or TypeScript, this has been built into the compiler. The people designing those languages had to do something special. They had to make a special case for if then else and say, okay, in this language construct, if then else, you evaluate the condition, and if it's true, you just look at the first branch, and if it's false, you just look at the second branch and you ignore the rest. In Python or TypeScript, it would be impossible. You can write a function like this, of course, but it would be impossible to get this short-cutting behavior. So if you write this in TypeScript as a function, so not using the built-in TypeScript if then else, but write a new function that you call if then else, then it would always evaluate both branches. It would still give the right result, but it would look at the else branch even if the condition is true. Because the rule in these languages is that if you evaluate a function, you first evaluate all the arguments. So it would evaluate the Boolean, it would evaluate the then branch and the else branch. And once it has evaluated all of them, it picks the right one. And the built-in if then else in TypeScript, for example, is a special case built into the TypeScript compiler or JavaScript compiler, whatever, to make a special case that for if then else, it doesn't behave like a function. It doesn't evaluate all the arguments first. The cool thing in Haskell is that it doesn't need to be built into the compiler. You can just implement it. So we can do these control constructs if then else with shortcutting behavior that are special cases built into the compilers of other languages. We can just define them as user-defined functions. And that's what Haskell also did. If then else is not built into the language. It's just, it wouldn't need to be. However, if we look at the next slide, there is special syntax for if then else in Haskell. So instead of using this function, you can write it like that. But that's not strictly speaking necessary. That's just syntactic sugar to make it look more natural. The point is in Haskell, you can define your own control structures, what you can't do in a lot of other languages. Other languages then use macros or stuff like that. If you want to do that in C or C++, you have to use a macro. But that's like another can of worms. And so this is, a very nice consequence of laziness, that you can define your own control structures. You can basically have full control over, you don't have to, you can ignore certain arguments if you want to, which you have no choice in other languages. So this is that. Are there any questions to this? I'm just checking. Oh yeah.
Yes, I got a question.
Yes.
In this last example, the if then else, we also have the result of error if we pass a undefined or
Sorry, if we pass a what?
undefined value.
Pass it where, you mean?
In the function, for example, if we call if then else, but undefined it as an argument in the else or the
Like
in the
I
then.
did here?
Yes.
Yes, I mean I did that here, right? So if a condition is true, and then it doesn't matter whether the else branch is undefined, it still gives me yes, which means it doesn't look at the else branch. It just evaluates the definition, the condition that is true, so it ignores the else branch. It doesn't matter that there's an error there.
But I mean, in the last example, when we are using the if then else that is already in the standard
Oh,
library.
it's the same behavior. So I can do, I mean, I can do exactly the same thing. X6. So I can. So if both branches are defined, everything is as expected. But now, for example, in the true case, I can have undefined there as well, and it still works.
Okay.
So yeah, it behaves exactly like this user-defined function.
Okay. Cool. Thank you.
Welcome. Are there other questions? We still have 10 minutes. Maybe I can, I mean, we can at least start with, okay. What about this? The guards I introduced earlier already at some point where we had this build function. So this is called a guard, these vertical bars. So you have your pattern here, but then you can have two or more or one or more lines with these vertical bars as a Boolean condition on the left-hand side, and then an expression on the right-hand side. And then if the pattern matches, it will check these guards one after the other until it finds one that is true. And the otherwise, I already told you that's just a synonym for true, which reads nicer in this case. One could just as well write true. It's just defined as true. Right. And I don't know whether maybe I can at least define the type. I mean, we can then revisit that on Friday. So this was now Boolean, and Boolean is, I mean, admittedly a bit boring because I mean it has two constructors, but they don't take any arguments. So a somewhat more interesting type is the so-called maybe type, and that's defined like this. So it also has two constructors. And the first one has no argument. It's called nothing. It's a parametric type, so it takes a type variable. And the second constructor is called just, and it takes an a. And in other languages, that's often called an option or something. So the idea is maybe a can be an a, in which case it's the just constructor, or not. I mean nothing. So it's often used in Haskell to indicate that a value can be missing. So for example, whatever, if you web programming or you validate a form, then maybe, I mean, let's say a form where somebody is supposed to enter their age. So it should be an int, but maybe the field is empty. So in that case, a maybe int would be, I mean, could be used to indicate that fact that there can be a value or not. I mean, in a lot of languages, null is used for this purpose, but maybe is much type safer. And so we have these two constructors. Nothing doesn't take arguments. It's polymorphic. It's like the empty list. I mean, the empty list is also list of any element type. and just takes an A and turns it into a maybe A. So I mean, we can of course try that out. So we can, for example, say just C. And that's of type maybe character, or we can say just yeah, it's of type maybe string, or just true of type maybe bool. And I mean, same as functions defined for Booleans typically have two equations, one for false, one for true. Functions defined on maybe will typically have also two equations, one's for nothing, one's for just. Maybe we can do one example, this from maybe, and then we stop for today. Let me hide. I know, I think from maybe, I'm not sure. No, it's not in the prelude, so we don't have to hide anything. So let's define from maybe. The type is A to maybe A to A. So the idea is we have maybe A, so that could contain a or not, and we give the default value basically. The idea is we want to, if there is an A in this maybe, then we want to return that A, but if not, then we want to use the default value. So the standard design pattern again. So we start with this type role. So now we don't know what to do. We introduce names for the variables. So let's call the one def for default, and then I don't know, MA for maybe A. So now we still don't know what to do. We know we must provide an A here, but we don't have an A. I mean, we have this def, but if we return always def, then I mean that's not what we want. It would be const. Right. So now the standard pattern, the standard trick is, or tip, to split cases on the constructors. So we have this MA of type maybe A. So we should look at, we can't do it for the first argument for the def because we don't know anything about A. It's generic in A, it's parametric in A. So we can't split by the def because we don't know what the constructors of A are. It can be any type. But we do know what the constructors of maybe A are. So let's split by that. So that can be a nothing, or it can be a just A. Also, as a side note, this A, that A are in different namespaces, so they don't clash. Because this A is a type and this A is a value. But often people use the same, the variable name A for something of type A, just to make it easier to see which is which, especially if you have like A's and C's, then it makes it easier. But I could just as well, name it X or so. There's no name collision because the types in Haskell live in the different namespace for the values. But anyway, so now we basically can answer this. So if we have a nothing, so there is no A in the maybe, in that case, we said we want to take the default value. So we can take the def. And in the second case, we do have an A, namely the one we called A. So we can ignore the default value and just give the A as an answer. And in that case, we don't even need to look at the default. Okay, and you can try it out, of course. So let's say our default, let's try characters. Our default is a lowercase x. So if I have nothing, then I get x. But if I have a just whatever, capital Q, then I get the Q. So that's, yeah, first example of a function on maybe. And it's a little bit more interesting type than bool, because also only has two constructors, but at least the constructor, the just constructor, takes an argument. So we'll see more examples of functions maybe in the next lecture, and then look at other types as well. Now, time is almost up. Are there any questions before we stop?
I think so far there are no questions.
Okay. Okay, then I think by now you should be able to do all the exercises, the first assignment, because that was only for this lecture 2 for the introduction. And
Yeah.
maybe already some exercises of the second assignment, but definitely the first. So I really urge you to do the exercises. As I said, it's important that you practice. Because often one listens to a lecture and thinks one understands everything, but then when you sit in front of the screen and your keyboard, you don't know what to do. So it's important to actually practice it. And I also noticed that shrunk quite drastically from 150 people to 15 people. I hope that this trend won't continue. But it also, of course, gives the advantage. So now if you're that few people, then of course we can take a lot of time answering your individual questions, and so please don't hesitate to ask. Okay, then
Yes.
if there are no.
One comment, sorry, Lars.
Yes, sure.
Some people couldn't access the assignments, and we believe that was because the organization asked to have two-factor authentication, and some didn't. So we removed that requirement, so that shouldn't be an issue anymore. And anyone that had any issue that didn't push the repository, I just removed the assignment, so you can just re-accept it and start like actually using it. So I think we shouldn't have any issues, technical issues anymore. And that's it.
Thank you, Robertino. So anything else? Then thank you. And we'll see you again
Hi.
on. Yeah, hi.
Hi.
Questions?
I'm trying to open my assignment through Visual Code, but the whole lesson is saying opening assignment.
Sorry, you try to open your assignment in Visual Studio Code, and what's the problem? I didn't catch that.
Can I share my screen?
I think so. I'm not sure whether you have the rights. You're more welcome to try. Or maybe. Do we have to just check? Maybe we have to do something.
I
Do you
think she
see
means the online. Yes.
Oh, it works.
Can you see it?
Yeah.
Yes, we can see it.
I have that problem of opening assignment.
You shouldn't need that that extension. Just the Docker development container extension. And once you accept the assignment, you can just use Git, the Git command line tool to clone it. And that will be it. Once you push to the changes to the repository, that's already synced. So there's no Visual Studio Code doesn't need to know that you're working with Classroom.
Okay.
Does it make sense? So if you clone the repository, you can just commit and push, and that will take care of everything.
Okay. Thank you.
Awesome. Yeah, you're welcome.
You're welcome. If you have more problems, just, you can contact us on Telegram, was it right? Or Slack. So just let us know if you're still struggling, then we can help you.
Yeah.
Okay, anything else? Okay, then I'll see you, hopefully all of you, or more than just you, on Friday.
Okay.
And
See
thank
you,
you very
everyone.
much.
Bye-bye.
See you.
Yes. Thank
Bye.
you, guys. Bye.
Thank you.